All right, simplifying radicals, level 1. When we're simplifying radicals, there's a couple different ways we can do it. The most common would just be to figure out what perfect square is a factor of this number, of the number inside the square root, the radicand. Um, but sometimes that can be a little tricky, especially if it's a really big number and you might not know your perfect squares super well. So what I like to do when that's the case is I like to do prime factorization. That's also called doing a tree diagram. That's what I think of it as. So when I'm looking at 20, you just want to think about what two numbers go into 20. So I break this up, and 20 can become, well, 4 times 5. And every time the number is as simplified as it can get, right? It's a prime number. I put a square root over it because I remember that, we're finding the square root of 20, not just breaking up 20 itself. Well, 4 can be split up into 2 and 2. Those are as simplified as we can get, so we square root those. Now, every time we have pairs, um, we're looking at the ones that have the square root around them. They're as simplified as we can get. So I have a pair of 2's. Every time we have 2 of them, the square root's going to cancel, and we're just left with the number on the inside. That's because when I have the square root of 2 times the square root of 2, that's going to equal the square root of 2 squared, right? Any number multiplied by itself is that number squared. And as we know, the square and the square root are inverse operations of each other. So whoop, gets rid of them, just left with 2. Right? So that's why that happens every time we have a pair. But when we don't have a pair, right, this 5 is all lonely, it's just going to be what I call the leftovers. So we have to make sure we multiply by the square root of 5. And that would be the simplified version of that one. All right, getting a little trickier. Number a little bigger, we got 48. You can think of any two numbers that go into 48. If you did 2 and 24, if you did 6 and 8, doesn't matter. We'll still get to the same answer no matter what. So let's say we're going to do 6 and 8. Well, 6 can get broken up into 3 and 2. Those are prime numbers. 8 can get broken up into 4 and 2. 4 can get split up again into 2 and 2. All right, so now we got to look at the pairs. Every time we have a pair, we write the number on the inside. I got a pair of 2's right here, so equals 2. Then we're going to multiply if we have another set of pairs. So I've got another pair of 2's, so I'm going to multiply times 2. And then we have our leftovers here, this square root of 3. Notice how I'm not touching this 4, this 8, or this 6, and that's because I only want to look at the numbers that are prime. So going one more step here, simplifying, 2 times 2 is 4, times the square root of 3, final answer. All right, let's try one last one. 72. We can break up 72 into 9 times 8. Keep going. 9 is 3 times 3, and 8 is 2 times 4. Right? 3 and 2 are as simplified as we can get. 4 breaks up into 2 times 2. So then we look for our pairs. I got a pair of 3's. So we got 3. I've got a pair of 2's, so multiplied by 2. And then our leftovers here is this square root of 2. Now I'm not going to lump this in with these ones because it doesn't have its own personal pair. So we leave that as the leftovers, square root of 2. So final answer would be 6 square root of 2. If we did have a tree where, let's say we have 2 square roots left over, so I'm looking at 3 square root of 3 and square root of 5 were my leftovers. Will we also multiply the leftovers just inside the square root? So square root of 3 times square root of 5, well, that is the square root of 3 times 5, which is the square root of 15.